Okay, Malthusian growth, and we'll see if this works. My phone's out of juice, so I'm charging it at the same time, but I'm not sure it's going to cope actually. I don't know which is using up, whether the charging gives more power than the video uses, but we'll see. So what's the idea here? What have we done so far? We've done the intro to the course, and then we had the first lecture, which was, what was that called? It was like technological change and technological progress and human takeover of spaceship Earth or something, wasn't it? And then we had, I think in that lecture, we had these different phases, didn't we? We had the Malthusian phase, and then we had the consumerist phase, and then we had this sort of technotopia possibility. And in the Malthusian phase, what did we say happened in the Malthusian phase? We said that, look, there's technological progress going on, and what happens when we have technological progress? Remember, it was like the blue ticks, yeah. When there's technological progress, we can get more of what we need out of our environment. Okay, so we've got this given amount of labour, we've got a given size of the population. With technological progress, we can get more food, more shelter, and so on. What happens, more of our kids survive. In the case of the blue tits, they breed more often. More eggs, more broods, and so on. More survive the winter, etc. Same for the humans. More of our kids survive. The population goes up, and that means with the given level of technology, suddenly we're back on the breadline. Okay, and at that point the population stabilizes. Then we get some more technological progress, and the population goes up again and stabilizes again. Of course, in reality, this is a continuous process, and then on top of that, we've got fluctuations. Like, you know, the Black Death comes, population goes down. Okay, but that's the broad story. So what we want to do here is actually capture that in a model. And at this point, we're not going to do that much with our model, I think, in this case. In general, why do we build models? Firstly, to be sure that we really understand what's going on instead of just a verbal reasoning. We're like, okay, let's assume this, 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 and this. What happens? That's one thing, so we really clarify our thoughts and make sure that it all does hang together logically. And the other thing is then to test what happens if this if this changes, if that changes, if we bring in some policy, whatever. Okay, but here we're really just gonna, I don't think we're gonna do any policy with this. We're just gonna see if we can build a mathematical model with the sort of properties we've talked about. I've talked about waving my hands around, talking about this Malthusian idea. Okay, so page 2. We want a model with what? Well, we don't want it to be unnecessarily complicated. So let's assume we've got a fixed amount of land. And it doesn't change in quality either, okay. And we've got a fixed basic needs. We need some quantity of consumption per person to survive, or more specifically, if consumption per person is at that level, which we're going to call y bar. So what's at the land area is called R. Basic needs we're going to call y bar. If we're getting y bar per person across the whole population, population will be stable. If we're getting more than y bar, it'll go up. If we're getting less than y bar, it'll go down. And then we need some growth function which is capturing this idea. And those of you who have studied or are now studying management of biological resources will know that we'll go for the logistic function. This is a nice function that we use, that it makes a lot of sense and it's nice and simple to work with. And then carrying capacity, which is a concept from these biological growth models, that will be determined by basic needs y bar in relation to the area of land and our own productivity. Well, yeah, and our productivity, how much can we get per person out of the land? That will depend on our technologies, yeah. And our productivity is going to change over time. And this is one thing we haven't talked about. Why will it change over time? We're going to link it to population. So the more people there are, the more people there are to have ideas, to do research, if you like. Of course, you know, the research department in the Stone Age village was probably pretty small, but people are still probably some of the time thinking, you know, how can we do things better? Not so much of the time, most of the time they're just getting on with it. But the idea is, with more people, we've got more people thinking, how can we do this better? More people coming up with new ideas, faster rate of technological progress. That's the idea. So those are the ingredients of our model. So then, what's the model going to look like? Page 3, and suddenly, whoa, a lot of equations. So I'm going to take you through these. Okay. So what have we got? We've got LT plus 1 minus LT. So this is population, is L, yeah? And the subscript, it's a discrete time model. The subscript is L at time t. And productivity, by the way, we're going to call RA with different subscripts. We'll get there in a minute. So this is the increase in population from one period to the next, isn't it? And we say it's theta LT 1 minus LT over LT star. Okay. So what's this telling us? It's telling us if LT is equal to 0 or very close to 0, this is 1, and we've just got LT plus 1 minus LT is theta LT. So which is basically saying if this is 0.01, that's saying the population is going to grow by 1%, isn't it? Because this is the extra numbers. Divide that by the initial numbers. You've got, if this is 100 and this is 101, that will be 1% growth, wouldn't it? And that would follow if this is 0.01. Yeah. So this is the growth rate when it's at its maximum point. But as LT goes up, this term starts shrinking because we're getting crowded here. And when LT equals L star, then there's no more growth. Okay, this is now population is at its long run level. There's no growth. Population will be stable. Okay. So that's our first equation. Second one is production. And we say y is ALL to the 1 minus alpha ARR to the alpha. Okay, so this is labour supply, this is the land area. So this is like population. And these are productivity factors. So if we get more productive in the labour gets more skilled, so to speak, that is going to raise productivity. But we can also get more skilled at using the area of land we've got in an efficient way. And if alpha is big, then this will make a big difference as well. Okay. What we're really interested in is production per person, yeah? And if we divide this through by L, we get AL to the 1 minus alpha AR. So we divided through by L. So, but then L to the 1 minus alpha. So we've got an L to the alpha left on the bottom line. So we end up with AR R over L to the alpha, right? Have I got that right? Yeah. Okay, so then if we're interested in production per person, then it's land area per person that is crucial, plus these two productivities. It all makes nice, perfect sense, doesn't it? And of course we call this a Cobb-Douglas production function, you all know that. But remember, L star was the stable population. So we must have that when y over L is equal to y bar, then L must be equal to L star, right? So then we must have AL to the 1 minus alpha, AR R over L star to the alpha. So we can rearrange that and say that the stable population, L star, is y bar over this, all to the 1 over alpha, AR divided by that. It's a mess, but we end up with AR R over y bar, I think. Yeah, over y bar to 1 over alpha times AL to the 1 minus alpha over alpha. Okay. And finally, what happens to technology? We could assume that we could let this grow as well, but for simplicity we just let this one be constant. It's not going to matter actually, and we let this one grow. So we just say, look, let's just set AR equal to 1. You could check this out if you want to, or you could just take my word for it. It's not crucial. Let's AL grow. So what's AL? We say ALT over ALT minus 1 is equal to, so this is the, how much, remember, yeah, so if this is 100 and this is 101, that's 1.01 it would be, wouldn't it? That would be 1% growth. Is equal to 1 minus delta. So far, there's going to be another term here, yeah. So what's this saying? If ALT over ALT minus 1 is just 1, that's saying AL is constant, isn't it? If we say this, then AL is going down, yeah? So what's this? This is depreciation. Basically, if we don't do any research, or if we don't put any effort into coming up with new ideas, our ideas are actually, the quality of our ideas and our productivity is actually going to go down, because we're going to forget stuff. Okay, so this will be small, but inevitably, if we don't do any investment in new ideas, we're actually going to end up forgetting the old ones in the very long run, and AL will go down. But, on the other hand, we have that somewhat tricky Greek letter is called zeta, and the one coming up, I'm sure you all know, is a capital omega. We have zeta omega L t minus 1 to the phi. So phi here is greater than 0. So the more people there are, the bigger this term will be. Okay, and this is adding to knowledge. Yeah. Or if you like, if you were to multiply through by this, this is a term that is multiplying our existing knowledge by some factor close to 1, but hopefully bigger than 1 if this is bigger than this, to make this go up. there's going to be some minimum level of population at which the new ideas, at which the productivity is constant, isn't there? And for population levels above that minimum level, productivity will go up. Whew! Okay. This is already turning into a long video, but we're soon there actually, because now page 4, I put some numbers on these. So we set alpha equal to 0.4. So this is like basically saying that the agricultural sector is super important. Again, that one really doesn't matter that much. Phi is 0.2, which means if you double labor, you multiply the production of new ideas not by 2, you multiply it by 2 to the power of 0.2, which is like 1.1 or something, 1.2 I guess. I'm not quite sure actually, what would that be? Whatever. Those are the kind of crucial factors. Delta is 0.02 and the time period is 20 years. So you're going to lose, every 20 years you'll lose 2% of your knowledge if you don't do any investment. Theta is 0.06. So the most the population can go up by in a 20-year period is 6%. Okay, which is pretty rapid actually, but I guess it's, yeah, maybe. Yeah, I mean it is 20 years, 6% in 20 years. Yeah, that's not unreasonable actually. The global population's been growing faster than that lately, in fact. Okay, and if we go on to page 5, when we simulate this model, what do we get? We match the historical data. Okay, so you get this very almost totally flat and then accelerating massively. So why is that? So when it's totally flat, the population is only just big enough to very slowly increase A. And when A is increasing very slowly, then L is increasing very slowly, then L star will be increasing very slowly, which means that this will be going down very slowly, which means L will go up very slowly, which means that not a lot will happen with technological progress, and we're still more or less flat here. But then as this starts to creep up, this term gets bigger, A starts growing faster, L star starts growing faster, L starts growing faster, L grows faster, this grows even faster, and we're into takeoff. And this is what's happening. Okay, so that's just showing you how you can actually sort of, okay, you can reason around Malthus, but this is showing, okay, assume exactly this, 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 and this. This is what happens, and then we can test if we can actually match some data. And it turns out we can, which is nice. Okay, and that is the end of the Malthus mini lecture, and the next one is megafaunal extinction, which we also, I think, talked about in the previous lecture. Super interesting.